In this video, we're going to talk about how we're able to predict whether or not a precipitate is going to form in a double replacement reaction, which will allow you to predict the state of matter of your products. So, one important thing to remember is that a precipitate forms in a double replacement reaction when one of the products is not soluble. So that's really the most important thing to keep in mind here, is when we talk about formation of a precipitate, we're really talking about a change in solubility. That if all of your reactants are soluble, but one of your products isn't, then it has to turn into a solid. So a precipitate forms when one product the reaction is not soluble in whatever solvent you're working in. So for us, that will be water. But the same rule applies in other solvents as well. So the product that is insoluble is insoluble, so it cannot stay dissolved. So it turns into a solid. So we can predict the solubility behavior of a compound based on the ions involved. So there are some patterns that we observe based on what cation and what anion are present in a compound. So we can predict solubility behavior based on the ions involved. So there's there are certain ions that tend to be soluble regardless of what they're paired with, and there are certain ions that tend to be mostly not soluble depending upon what they're paired with. So essentially, compounds involving certain ions are generally soluble, and those involving other ions are generally not soluble. So there are patterns that allow us to make these predictions. And the collection of these patterns is commonly known as the solubility rules. So this is a simple list of the solubility rules. There are certainly others. There are a lot more ions in the world than just these, but these are some of the most common ones that you'll encounter. So this is more than enough for you to get a sense of what these trends generally look like. So note that the top half is things that are generally soluble. So this is things that can dissolve. And this is specifically talking about in water. And then down the bottom, we have the compounds that are generally insoluble. So compounds involving these ions generally cannot dissolve in water. But you will notice in both cases, in both cases, we have exceptions. So for many of the ions there aren't any, which is nice. It's always nice when there are no exceptions to the rules. But for certain ones, we do have lists of exceptions. Now, the exception lists down here look long and confusing, but really they're just some of these. So the group 1A metals, lithium, sodium, potassium, rubidium, and cesium, are always soluble with no exceptions. So those are all down here as exceptions to things that are generally not soluble. So what we're looking at is we have a list of things that are usually soluble, will usually dissolve in water, unless they're paired with something on these short lists. And then we have a list of ions that are generally not soluble unless they're paired with some of the ions on the exceptions list here. So having these rules allows us to make some predictions about whether or not a given reaction is going to form a precipitate. So let's look at a couple examples of how we predict whether or not a compound is going to be soluble and use that to figure out whether or not you will have a precipitate form in a chemical reaction. So we're going to do two examples. And for each of these two examples, we're going to finish the double replacement reaction, which you've done before. And then this is where the new stuff comes in, that we're going to predict whether each product will be aqueous or solid using the solubility rules. And then we'll write the net ionic equation, which is also a review from a previous video. So our first example is going to be reaction between lead nitrate and sodium chloride. So take a minute here and try and finish that reaction. So just do step one. You don't need to put in the states of matter yet. I'll talk you through that part. So for finishing our reaction, we're going to want to think about what all of the charges on our ions are to make sure our formulas for our products are correct. Nitrate is always -1. And in this compound, there are 2 nitrate ions, each with a -1 charge. So we have 2 negative charges overall, which means that the lead must have 2 positive charges to balance that out. So lead is one of those uncertain ions. It can have multiple different charges, but we can use the charge of nitrate, which we know, to figure out that the lead must be +2 here. Sodium is in group 1, so that'll be +1. Chlorine is in group 7, so that'll be -1. So when we switch our partners, lead is going to end up paired with chloride, and sodium is going to end up paired with nitrate. So if we think about our charges once again, we have +2 with -1 and +1 with -1. So +1 with -1 is fine, and NaNO3 is the correct formula for sodium nitrate, but +2 with -1, no good. So we're going to have to add a subscript after the Cl to balance that charge. So the last thing we need to do is make sure that the reaction is balanced overall. And to do that, we will just need, currently we have 2 nitrates over here and only 1 on the right. So we can add a coefficient of 2 in front of the sodium nitrate. And then we currently have 2 chlorides over here and only 1 on the left. So we can put a 2 in front of sodium chloride, which also gives us 2 sodium, and we just made 2 sodium over here. So this reaction is now balanced. So to determine whether each of these products is soluble or insoluble, we're going to want to consult the solubility rules. So looking at our first product here, we have lead and chloride are our 2 ions. So if we go back up here, take a look at our solubility rules, you will find that there is no rule specific to lead, but we do have chloride right here. So chloride is in the usually soluble category. However, lead is an exception. So that means that when chloride is paired with lead, it's not generally going to dissolve. So that would be an insoluble compound. So this is insoluble. Chloride is usually soluble, but not with lead. But lead is an exception. So if something is not soluble, that is when it's going to be solid. So things that become solid when they're produced, or things that precipitate, are those that are not soluble in water. So this is going to be solid in this reaction. Now for the other one, for sodium nitrate, if we look back at our solubility rules, we see that there are rules for both sodium and nitrate, and they're both soluble with no exceptions. So sodium nitrate is definitely soluble. Both Na plus and NO3 minus are always soluble. So anything soluble is going to remain dissolved in solution, or aqueous. So this will be aqueous. So then the last thing that we can do is to use this to write the net ionic equation. So what the net ionic equation does for us, in short, so in a previous video, we kind of went through the whole process of going from the molecular to the total ionic to the net, but we can skip over the total ionic if we understand that what the net ionic is showing here is that it shows the formation of the precipitate from ions. So the reactant side of the net ionic equation is always going to be the cation and the anion when they're still dissolved in solution. And then the product is just going to be the solid precipitate. So if we want to write our net ionic equation for this example, our precipitate is the solid, is this lead 2 chloride, this PbCl2. So what our net ionic equation is showing us is producing that. So our only product should be that solid precipitate that we formed, and then we just need the reactants to be the ions we needed to form that. So we would need a lead 2 plus ion, and we would need 2 chloride ions. Those are the components that came together to form this precipitate. So we can apply this same process to one more example. So let's see if we can go through the same thing for potassium carbonate and calcium bromide. So go through that same process we just did for the first example, completing the reaction, balancing it, identifying each product as soluble or not soluble, and then writing the net ionic to show the formation of that precipitate. So to finish this up, first thing we're going to want to do is have our ions trade partners. So we will get KBr and CaCO3 as our two products. If we go through all of our charges, potassium is +1, carbonate is -2, calcium is +2, bromide is -1. So the way I have them paired up over here, everything is all set in terms of our formulas. We don't need to add any subscripts. Everything is in a 1-to-1 ratio in our products, but our reaction is not quite balanced. So we can balance it by just adding a 2 in front of KBr, and then it is all set and correct. So the next thing we want to fill in is whether our products are going to be solid or aqueous, whether we're going to have a precipitate or not. So if we look back to our solubility rules, let's look for KBr first and see if we can figure that one out. We find that potassium is soluble with no exception. So we don't even really need to think about the bromide. We can. It's down here. It's usually soluble, and potassium is not an exception, so that makes sense. But if you recognize that potassium is always soluble, that's as far as you actually need to get. So for this example, KBr is soluble. So that means it will stay dissolved. It will be aqueous. Then for our other one, calcium carbonate, if we go look for this, we will find that there is no rule for calcium specifically, but we do have carbonate down here as something that is generally not soluble, and calcium is not an exception. So remember that in this case, the exceptions would be things that are soluble. So calcium paired with carbonate is not, so it follows its typical trend of being insoluble in water. So calcium carbonate is insoluble, which means that it will produce a solid precipitate. So if we want to write the net ionic, that is what we're going to be showing the production of. Our net ionic is going to show calcium carbonate forming from its ions, because that is our solid, that is our precipitate. So our net ionic will show calcium carbonate forming from its ions, which are calcium 2+ and CO3 2-. So those ions were dissolved, and now they stick together to form calcium carbonate as a product.